Well, hey guys, here we are for some distance learning, right? So the main plan for today is to do some review of molecular polarity, all right? And so basically, again, the overall idea is to be able to relate molecular formulas and structure to the properties of a material. And really, we're going to focus in on structure for today. All right. So some quick rules to remember. So we did already discuss this in class. Hopefully you remember and already have it written down. But the rules to remember is that just because we have polar bonds does not mean that it is necessarily a polar molecule, right? So polar bonds, right, if you recall, is referring to the bonds that we have in our material. And if that electronegativity is greater than 0.4, right? Then we have polar bonds. So in the case of the carbon-oxygen bonds, right, that electronegativity is greater than 0.4. So we have polar bonds. Okay, we do not have a polar molecule because, right, we have balance on both sides. We have polar bonds here, and we have polar bonds there, and those are balanced. Okay. Now, if we contrast that with formaldehyde over here on the right, okay, we have to, in order to have a polar molecule, right, we have to have some asymmetry in the molecule. So this is symmetrical because we have a balance in our polar bonds on both sides. Whereas over here, so we have carbon-hydrogen bonds, which are non-polar, right? We have carbon-oxygen bonds, which are polar, all right? So we have an imbalance in our polar bonds, and we have those lone pairs on one side. So this is an asymmetrical molecule over here, right? That's what makes it polar. So the symmetry or asymmetry of the overall molecule is what determines it to be polar or non-polar. All right. Now, symmetry versus asymmetry. How can we tell just by looking at the molecule, right? So a molecule is symmetrical if the following things are true about it. Number one, none of the bonds are polar, right? So in the case of methane, CH4, we've used this example in class a few times, right? All of the bonds are carbon-hydrogen bonds, right? So the bonds are non-polar because they have a difference in electronegativity of only 0.4, right? That is not enough to designate those bonds as polar. So all of the bonds are non-polar. Therefore, automatically, we have a symmetrical molecule. Now, sometimes, like I mentioned before, we can have polar bonds, right? But if they are balanced, we are still symmetrical. And again, we'll go back to that carbon dioxide, right? So we have polar bonds here, balanced out by polar bonds there, okay? And likewise, if we were to draw our lone pairs on here, so we got 1, 2, 3, 4 lone pairs there, balanced out on both sides. We also have 2 lone pairs on the oxygen side over here, right? So because of that, like again, if we were to draw this, a line down the middle, we've got symmetry on both sides. Same thing goes for this direction, right? It all looks the same on all sides. So this is non-polar, and this is also non-polar. Even though we do have polar bonds, they are balanced in carbon dioxide, therefore that molecule is nonpolar. Now, so a molecule is considered asymmetrical, right? So we have some asymmetry in our molecule if at least one of these is true. So if the polar bonds are not balanced. So going back to that formaldehyde example, right? We've got non-polar bonds between carbon and hydrogen, right? And we have polar bonds between carbon and oxygen. So we end up with part of our molecule having polar bonds and the other side of that molecule having non-polar bonds. So they are not balanced, right? Likewise, we could end up with a molecule in which the lone pairs are not balanced. So again, with our formaldehyde, you'll notice that our lone pairs are isolated to one part of that molecule. Okay, so therefore we have no balance or imbalance in our lone pairs. That also makes it asymmetrical. Okay, now the one other thing that can cause asymmetry, right, is it's not so much an imbalance in lone pairs, but if the lone pairs are only found on that central atom, we end up with, right, a region of more negative charge because electrons, as you all know, are negatively charged. And so if we have a bunch of extra electrons on one part of our molecule, right, that makes that part much more negative than other parts, right? So we have an imbalance in those charges. So asymmetry is really referring to, do we have a part of the molecule, a region of that molecule that is more negative than the other part or other half of that molecule? If that's yes, we have asymmetry. Asymmetry means polar. All right, so here's what you need to be able to do. So again, we're talking test, quiz type situation, right? You need to be able to draw Lewis structures like we've been practicing in class, okay, using that honk 1, 2, 3, 4 method or the electron transfer method that we use for ionic compounds. 2, you need to be able to identify the bonds as polar or nonpolar. Again, that's where we're looking at that electronegativity. If it's greater than 0.4, we are calling it polar, right? If it's less than 0.4, right, we're calling it nonpolar, okay? And 3, you have to use symmetry or asymmetry. So again, getting interrupted by my 6-year-old here, but again, we want to identify a molecule as polar or nonpolar based on the symmetry of the overall molecule, not just the types of bonds that are present. Okay? So let's do a couple of examples, right? So we have ethanol. Now, if you'll notice, these are actually both have the same. Okay, so both ethanol and dimethyl ether, right? One thing that you might notice is they actually have the same numbers of carbons, the same number of hydrogens total, and the same number of oxygens. So for example, this is, they both have 2 carbons. So there's our 1 and 2 in dimethyl ether. There's our 2 in ethanol. Both have 6 hydrogens. So we got 5 plus 1 more makes 6. 3 plus 3 makes 6, and 1 oxygen. Now, they're written a little bit differently to help show you that they actually have different structural formulas, right? So again, just because it has the same number of everything doesn't mean it's always drawn the same way. So we could draw C2H6O in a couple different ways. One is as ethanol, the other is a different molecule called dimethyl ether, right? So we're going to go ahead and draw both of these, right? So the reason I wrote OH over here like this is to indicate that that oxygen has 1 hydrogen attached to the oxygen, okay? And so the way we would draw ethanol is we're going to go a C, another C, right? And then I'm going to have an OH on one side. Okay, I'm going to go 1, 2, 3, and 4. All right. Now I'm also going to go ahead and add my lone pairs on my oxygen. Right. We want to stay in the habit of doing that. Okay. Now, what we want to look for here is our bonds, right? So again, we have our carbon-hydrogen bonds. So those carbon-hydrogen bonds, as we indicated earlier, this is being stubborn, are non-polar. All right. So all of our carbon-hydrogen bonds are non-polar, but we have a polar bond here, and we have a polar bond there. Okay. So the question is, are those bonds balanced overall? Right? So if we were to look at one side of this molecule, or is there one side with more polar bonds? And that is a yes, right? We do have more polar bonds on this side, and we have unbalanced lone pairs. So this is a polar molecule. Okay, now I got a different color. So now, if we contrast that with dimethyl ether, right? So we wrote it this way to show that we have carbon with 3 hydrogens attached to an oxygen, which is attached to another carbon with 3 hydrogens. So we're going to write it like this. I'm going to put an O in the middle. The C, 1, 2, 3, H, 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 and I have to apologize, I lost my magic pen, so I'm trying to do this with my finger. All right, and then a C over here with 3 H's. H, H, and H. Right, and then a couple lone pairs. Whoops. On our oxygen. Sorry about this. This is so much easier when I have my pen. But, okay, so there's our 2 lone pairs on our oxygen. Right. So now we have polar bond here and a polar bond here. Right? But that's balanced. Right? It's polar on both sides. So there's no imbalance in polar bonds. Now, we do, however, have an imbalance in our lone pairs right here. So on that oxygen, which is our central atom, we have some lone pairs. So even though we have balance in our polar bonds, we have imbalance in our lone pairs, which would also make this molecule polar. Okay? So again, to be symmetrical, right, we have to have complete balance in our lone pairs and complete balance in our polar bonds, right? So in the case of ethanol, we're asymmetrical for 2 reasons. There's imbalance in polar bonds, right, because they're only on one side, and there's imbalance in lone pairs. In the case of dimethyl ether, right, we have balance in, so we're symmetrical with our bonds, right, but we're still asymmetrical because we have a imbalance in where the lone pairs are found, which is only on that central atom in this case. So both of those we would call polar. All right. Now, moving forward in our next lesson, so after you've had some chance to practice this, right, we're going to take all this information so we can look at the formula of a molecule and look at different ways to draw it. And if it turns out that that molecule is polar or nonpolar, right, we should be able to start making some decisions about, or predictions, I should say, about the relative melting and boiling point, right? Whether or not it has a distinct aroma, whether or not it will dissolve in water, whether or not it will conduct electricity, right? So we're going full circle, right? We started the unit looking at this. We learned a whole bunch of chemistry about electrons and formulas, right? And we're cycling all the way back to that, okay? But now you guys will be able to explain all this. By the end of this unit, explain why certain molecules have certain properties. All right. Anyways, that is the end of this lesson. Your job next is to go do some practice with molecular polarity, right? Again, using that honk 1, 2, 3, 4 method, identifying what types of bonds and where your lone pairs are. Is it symmetrical or asymmetrical, and therefore is it polar or nonpolar as a molecule, etc. All right.